So, our lecture for today, we're going to talk about how it is we actually make a map, some properties of maps, and how it is we are converting our globe, which is three-dimensional, into a two-dimensional representation. And this is through the process of projection, which you only need to know a little bit about, but it's kind of important in GIS. So we're gonna talk about that. All right. So these are our tasks for today. This is probably one of a couple technical talks that I'm going to give you this semester, so that you can learn some things that you've probably never had in any other class. So we're going to talk a little bit about basically how maps work. Some of you, if you've done stuff with maps, particularly if you've used topographic maps or something like that, you may be familiar with some of these things. If not, this is going to be essentially a good review for this, and I do test a little bit on this, but not particularly much. So to start with, we want to talk about scale in maps, because that's actually, of all the things I talk about today, somewhat the most relevant, because at what scale you're working at makes a big difference. Maps are the question you're going to answer or ask is going to have could be addressed at multiple scales, and you might get different interpretations, different answers at different working scales. And so trying to decide what scale is the best, or what scale you want to explore this with, or if you need to explore this at multiple scales, that can make a big difference. Now, the most basic type of scale, and one of which you will see in ArcGIS, is a ratio scale that is essentially dimensionless, right? Because it can be any units, and it's written like a fraction, or it's usually written like a colon like this, so a slightly different kind of fraction. So 1 to 24,000. It's a very common map scale. That's what the U.S. Geological Survey publishes most topographic maps at that scale, 1 to 24,000, which means that anything on the map, one of them, it could be an inch, it could be a foot, it could be your foot or your hand. It doesn't matter, because there are no units. But any one thing on the map equals 24,000 of those in real life. So if it was inches, and that's kind of the way we think about things, 1 inch on the map would be 24,000 inches on the ground in real life, wherever that map is. Or if we divide 24,000 by 12, we get 2,000 feet. So every inch on the map equals 2,000 feet. Another way to say that scale. All right. So this is a fairly useful, fairly straightforward way to do this. You'll be able to see this in ArcGIS. You'll be able to set this in ArcGIS. And if we're dealing with a map like this, which encompasses most of the world, this is at 1 to 100 million scale. So this is a very small scale map, right? Because this fraction ends up being a very small number. 1 over 100 million is a tiny, tiny number. And so we can see most of the world at this scale, but even at this scale, we can't see the entirety of the world. We're cutting off about half of Asia over here, most of the Pacific Ocean over here. So it doesn't get quite the entirety of the world, but there are lots of things we might want to look at a scale that's up around, this amount, or 1 to maybe 250 million. You might be able to get more of the Earth in, almost all the Earth in at that point. All right. Then we can have large scale maps. Large scale maps show small areas. Small scale maps show large areas of the Earth. And that can be a little confusing. Just keep in mind that fraction, that 1 to whatever, the bigger the number, the smaller the fraction, right? 1 divided by... Are you serious? Like, why are you doing this? Yes, I'm still using the system. Thanks. You're super helpful. All right. So here we have 1 to 10,000 in a couple of different places. This is Pittsburgh over here. I think this is Manhattan over here. So you could see at this level streets and things like that. 1 to 10,000 is another fairly common number. It's a nice number to work with. 1 to 10,000. It's pretty localized effects that you're going to be looking at here. This could be how could be the scale you want to work at, especially if you're interested in what's happening sort of block by block in a city, especially a small city. This might encompass the entire town. So 1 to 10,000 could be pretty useful that way. All right. Now, the next thing we got to talk about are coordinates, and how do we represent a position on the Earth? So what is the sort of standard way that we talk about a location on Earth? What do we talk about? Yeah, latitude and longitude. Latitude and longitude are a type of spherical coordinates, okay? And so you have to remember the Earth is a sphere. This is why we use those. There are other coordinate systems, and depending on the kind of map we'll be looking at, there will be different kinds of coordinate systems that we can use. But a spherical coordinate system is designed to work in 3 dimensions. It's working in the fact that the Earth is roughly a sphere. I don't think we'll get into the details of the geoid, which is the actual shape of the Earth, and trying to model mathematically what the actual shape of the Earth is. Roughly, the Earth is a oblate spheroid, which means it's close to being a sphere, except it's a little bottom heavy. It's a little fatter in the southern hemisphere than it is in the northern hemisphere. It's a little stretch down there, just the way the Earth spins. It's like that. So that can be important when we're trying to figure out where precisely we are. For a map, it doesn't matter quite so much, but we got to practice a little bit with spherical coordinates. Now, you guys may have seen, maybe a little bit familiar with latitude and longitude. How many people have seen latitude and longitude for different kinds of places? All right. So typically we report things in terms of latitude and longitude, and it's important to keep those in mind, which is which, because they actually have slight differences. Okay. So, for example, Pittsburgh here is roughly 80 degrees west. So this is the 0 east-west line. All right, so that's its longitude, and roughly 4 degrees. So from 0, which goes through Greenwich. So this is what's called the prime meridian. This is the 0 line, goes through England. It was set up here by the Brits back in the late 1700s. They decided 0 should be right here. There's actually a line on the floor at the Royal Observatory where 0 is, and from there we measure everything else. So we measure, well, in terms of longitude, we measure everything else. That's arbitrary. Longitude is arbitrary. The British just picked a point, and everybody decided that was fine, and so have been working off that ever since. 0 latitude, however, is what? The equator, and that is a real place. That's the widest point around the Earth, in this direction, essentially, sort of perpendicular to the poles. It's the widest point around the Earth. So Pittsburgh is also 40 degrees north of the equator, and we need to specify those 2 directions in order to get to the right place. West and north will get us to Pittsburgh. If we go east and north, we'll get somewhere else. If we go south and west, we'll get somewhere else. So all of those actually make a difference. All right. So here is latitude, and keep in mind which is which. It can be a little confusing. You gotta remember latitude. I like to think latitude is flat. Latitude is flatitude. Latitude's flat. So we measure in this direction. There are 90 parallels, or 90 degrees north and south. So we go up away from the equator. 90 is the north. 90 north is the North Pole. 90 south is the South Pole. These are called parallels because these lines are always parallel, right? And if you notice, they don't curve or anything. They are straight around, which means they actually change size. The closer you get to the poles, the shorter it is around the Earth. So if you really want to walk quickly around the Earth, you just go to one of the poles and walk around it. You can get around the Earth real fast that way. Go around the equator, that's the longest way around. All right? Works a little different for longitude. So, wait, do I not have? Oh, I must have skipped over longitude. Okay, so longitude starts at the prime meridian, which is 0. and then goes all the way around the Earth to 180, which goes through the middle of the Pacific. And so we go 180 degrees this way and this way. The Earth is essentially 360 degrees around. It's a circle. So each one of these is a great circle around the Earth, which is why they're curved. Right? So they're roughly similar in size to the equator. The equator is the only one in this direction that goes all the way at the widest point around the Earth. Right? And these are called meridians. Okay, so the prime meridian meaning the first meridian. And this divides the eastern and western hemispheres. Right? The equator divides the northern and southern hemispheres. All right, so let's look at some points on a map. All right, now because we're dividing up things into degrees, we often report more exact measurements of where we are in degrees and minutes and seconds. Okay, so kind of just a function of subdividing, it is related in a sense to time too, because it takes 24 hours for the Earth to go around, or the Earth to turn all the way around to make one rotation. It takes 24 hours. And so if we divide the Earth up into 24 slices, each one of those, it's going to take basically an hour for time to pass in each one of those. And those would line up somewhat with these with the meridians, not entirely. I mean, it would be every hour's worth basically as we go around. So it's also related because of geometry. If we're dividing up a circle, we can divide up a circle easily relatively easy into 60 parts. It's like using a protractor, and when maps were made by hand and you would navigate on a map by hand, you would use a protractor or a compass to measure and move around the map. So we need to think about degrees and minutes and seconds. Not very much, but just a little bit so that we are aware of it. All right. So Pittsburgh, more precisely than 40 degrees north and 80 degrees west, is 40 degrees, 26 minutes, and 2 seconds. Adelaide, which is in the opposite hemisphere, so in the southeastern hemisphere as opposed to the northwestern hemisphere, is 34 degrees, 55 minutes, 44.4 seconds south latitude. And then this is 80 degrees west. This is 138 degrees east. Okay? So keep in mind, every degree can be divided into 60 minutes. Every minute can be divided into 60 seconds. And that works for both the latitude and the longitude. Any questions so far about latitude and longitude and degrees, minutes, seconds? So every second is 3,600th of a degree. If we divide a degree by 60 and then divide again by 60, so 60 times 60 is 3,600. Okay, good. All right. So let's look at this. While degrees, minutes, and seconds are commonly used, they're actually kind of awkward because they're like 3 separate numbers. And it's a lot easier for a computer. It's actually a lot easier for us too, I think, to deal with one number instead of 3 different numbers. So while a lot of data is reported in degrees, minutes, and seconds, ArcGIS can't really do anything with that. And we have to convert that into what are called decimal degrees. So we have to take the degree, the minutes, and the seconds and convert those parts into a decimal. Right? It's not going to change the degree number. That's still the same. So if we look, as an example, is the latitude of Pittsburgh. So 40 degrees north translates to 26 minutes and 2 seconds. So 26 out of 60, we can make a fraction out of that, right? We can divide 26 by 60 and we get 0.433 repeating. We can also divide 2 by 3600 because there are 3600 seconds in a degree. So 2 divided by 3600 gets 0.000, wait, 3 O's, 0.00055. And if we add them together, we get the number rounded 40.434 degrees. All right. So your turn. Let's see what you guys can come up with for the longitude. Oh, wait, I've given you the longitude for Pittsburgh. Oh, I didn't give it to you the other way. I thought I did. Oh, well. I did not. Oh, well. So we should at some point practice this. I used to make you guys. Maybe I decided I didn't want to make you practice this anyway. So I can make you convert it back. That's I think a little harder, but it's easier going this way than back the other way, because back the other way, you gotta like figure out the rounding. It's a little bit more messy. I don't ever make you do it this way, but make sure you practice this once or twice, so you can get used to it. Now you can find online programs that'll do this for you. You can easily write this formula into Excel if you have separate columns for separate sets of numbers for degrees, minutes, and seconds. But if you get data this way, you'll have to convert it to this format in order for ArcGIS to know what you're talking about. Now, because latitude is in north and south, then there's north numbers and south numbers, and longitude is in east numbers and west numbers. We could have not done that for longitude. We could have just done, well, we could have not done it for, it makes less sense if we didn't do it for latitude. It makes less sense to it makes sense to have north and south. That's like a real thing. But east and west are kind of arbitrary. So we could have just done 360 degrees, and then we could have skipped having east and west. But the important thing is that in order to deal with that, we use positive and negative in decimal degrees. So we're a little biased. Here in the northern hemisphere, we're positive, and the eastern hemisphere is actually positive. The western hemisphere is negative. So Pittsburgh in decimal degrees would be 40.434 and negative 80.016 degrees. So keep that in mind. North is positive, south is negative, east is positive, west is negative. And if you don't have those numbers right, if you flip those around or do something, all of a sudden your points are not going to go onto your map in the right spot. You'll zoom out and go, oh, wait, why is this stuff way over here? That's not where it's supposed to be. And you'll have to change the sign of your numbers, basically. That's right. Mm-hmm. And so you need that, even though we might be used to just talking about 40 degrees, 80 degrees west, and not saying the negative part. If you say west, you don't need to say the negative part. If you don't say west, and ArcGIS, you can't tell it west. You have to tell it it's negative 80 so that it goes the right place. All right. So what is somewhat interesting about this is because of the rough shape of the Earth is not completely spherical. There are some differences in the size of these things. All right. So if we go, the circumference through the poles is 24,859.82 miles, and the length of the equator is 24,901.55 miles. So it's a little bit wider around the equator than the Earth is. The Earth is a little short compared to how wide it is. And that makes some slight differences. So a degree of latitude is 69.1 miles roughly. And you divide that by 60, it's roughly a little over a mile for a minute, and a second is at roughly about 100 feet. So not quite a little bit more than 100 feet. These aren't super important that you know these. It's just know that the Earth changes a little bit. And as we'll see next time when we work with some topographic maps, the lines of longitude get closer together the closer you get to the poles. And so they change dramatically how big a longitude line. The latitudes lines are all equally spaced. So they stay the same. You can't do this for longitude because the widest space between 1 degree at the equator is a much bigger number than it is at the pole because it eventually goes to a single point. So eventually that's where they meet and touch. So there's no space between them. So it's everything from touching to what would be close to this. It would be close to that. So about 69.1 miles apart, each degree of longitude. So longitude varies quite a lot, how much distance that actually represents. So wherever you are is going to have a slightly different number because of that. Okay, so we have some basic things. We have our spherical coordinates that we use, latitude and longitude, to point out where we are on the globe. But we're going to need to convert that, and we're going to need to think about making a map from the globe. And that's where map projections come into play. Map projections are something that mostly happens in the background, although can make a big difference in how your map looks, because this is a way of representing the reality of Earth. The Earth is a sphere. It's closer to a globe than it is to a map. And in order to get that to actually something that we can see, we're going to have to use some math in order to essentially stretch, compress, change the surface of the Earth to 2 dimensions. Now, there are actually literally hundreds of map projections. There's hundreds of different ways to do this because you can center the map in slightly different ways. You can hold some things constant versus others. We're going to talk about some of the most common ones and reasons why you would select one over the other. All right. So every projection is a set of compromises, which is another way of saying they all have advantages and disadvantages, but they are all compromises because there is no way to make something 3-dimensional, 2-dimensional without introducing some kind of error or bias. We're going to stretch things or alter things or change things. So which projection you select in part depends on the scale of the map. All right. The smaller the scale map, right, the more area of the map you're showing, the more this actually matters. It really doesn't matter so much when you get down to a scale like 1 to 10,000 or even 1 to 24,000. It doesn't make much difference. Things are not going to look, they're not going to show up much different than that. And in fact, you won't even be able to detect what kind of map, because at that point we're zoomed in so close, we're not going to notice things like the shape. The shapes aren't going to be very much off. So scale matters. What projection you select matters more. The smaller the scale map, the more it matters, because then you start to see bigger differences in those things. What you're going to do with the map, or what you're going to try to illustrate with the map, makes a big difference as well. That's essentially the second consideration you take in mind. Different kinds of projections can be centered on different places. If you want to make a map of the poles, if you want to make a map of Antarctica, you would select a very different projection than if you wanted to make a map of North America or the United States, because they're very different parts of the world. You're going to see a much bigger effect. So there is maps that are appropriate for the poles. There's maps that are appropriate for other latitudes because of that. All right. Now, sometimes it makes a difference too, which map, what you're trying to either measure or describe. There are maps that preserve different things. If you're trying to navigate, you're going to want a map that preserves direction. If you want to measure the size of something, you're going to want a map that preserves area. If you want to just show the Earth in its most sort of in a nice, accurate way, you might want some distortion of all of those things, just so the map looks a little bit better and a little bit more normal. All right. So let's look at some ways that we can project the map. All right. So we're not actually flattening a ball or something like that. What we're doing, the reason these are called projections, is you need to think about essentially slices that are, say, like we're shining a light through the Earth, and what if the land is the shadow or something like that, it's going to cast the shadow on that, and that's what we're drawing. That's why they're called projections. We're sort of putting this three-dimensional surface onto a two-dimensional surface, and in some of these cases, we put it onto a three-dimensional surface that we then change, we then flatten out. So for the first kind are planar projections. All right, these kinds of map projections we put onto a tangent plane. So that's a plane that touches the Earth in one spot, or a secant plane that like goes through the Earth at a place, and then put the map on it there. Right? Cylindrical projections, we wrap the Earth in a cylinder, and depending on what we want to show, we could wrap the Earth around the equator, and we're going to touch the Earth basically in a line. In this case, this will touch the Earth in a point, or if we cut through it in a circle of some kind, this will cut the Earth. The Earth will touch the map on a line, and so we can also put the cylinder through the Earth. So it's usually tangential, but we can also do it through secant. We can go through the Earth, and then we cut it and unfold it. We can change the orientation of the cylinder as well. So if we were looking at, this works good if we're looking at sort of the middle latitudes, we would turn the cylinder and unwrap it if we wanted to look at one of the poles. So there's lots of different ways. And then we have conic projections. And so in this case, this works good for things that are sort of in between either the poles or the equator. And this often makes this can also preserve area better than some of the other projections can. So this is often used for that kind of a map. So these are three basic ways of cutting these. And so there's a couple of things to note about map projections. There is no distortion where the surface touches the Earth. But as I said, in a lot of cases, that's just a single line. There's not going to be a lot of area that is free from distortion. Secant projections go through, and then if we rotate, we can talk about the same kind of projection, but being transverse if it's turned 90 degrees. So for this, that mostly comes up with a cylindrical. I'm going to come up with it. Well, it doesn't make much sense with this. You turn that 90 degrees, it's the same. You turn this 90 degrees, and the cylinder goes around the Earth, this way. You turn this cone 90 degrees and go this way. All of which make different kinds of maps and have different kinds of effects. So the first of these is what's called a conformal projection. This is based off of a cylindrical projection, and this is the most common kind of map, or a map that you may be the most familiar with. The classic example of this is the Mercator projection, which was developed, actually probably predates this, but it's named after one of the earliest maps of the world that was done by a guy named Mercator, who used this projection to make his map. It's fairly straightforward because you just wrap a cylinder around that touches the Earth at the equator, and then you peel it out. Now, because of that, you get some serious distortions. All right, because all of those longitude lines meet at the poles, you then stretch them all out, and you get essentially infinite distortion at the poles. The equator is just fine. Everything else gets radically distorted, which is why on a map like this, Greenland looks bigger than South America, even though Greenland is less than half the size of South America in real life. Antarctica looks gigantic on this projection, and they usually cut these off so that you sort of are not seeing the worst of these effects. Mercator preserves angles and shape so that east and west is the same scale as north and south. These maps are useful for navigation. If you're sailing from the old world to the new world, back in the 1500s in the Age of Discovery, you needed to use this kind of a map so that you would know where you're going. Although back in 1569, there was no way to measure longitude, so you kind of had to guess how far you'd gone, east or west. We couldn't measure it back then. That's a whole other story. Anybody know how they figured out how to measure longitude? Nope. That's what they thought, and that never works. Latitude you can measure with the stars. And so you can tell how far from the equator you are by that. Oh, well, you would measure that with a sextant, but you need something else. Nope, not magnets. Magnets will, you can use a magnet to figure out which way is north. That's useful. So you use a compass to figure that out. That would point towards the magnetic north. You actually have to use time, and that was a huge invention. Was a clock that would accurately keep time. And so a sailing ship, it would set its clock. It was if it was coming from England, for example, set its clock to what zero longitude, what time the sun would rise at zero longitude. It would have the time of Greenwich. Then the farther east or west you got, the sun would either rise earlier or later by that number of hours, and that would tell you how much longitude you'd gone. And it wouldn't actually matter how far north or south you were. Well, it kind of does, but there's like that's like a second. No, it actually does matter how far north or south you are. So you have to know that first. So you have to know how far you are north or south. Then you can figure out how far east or west you are based upon the local sunrise or sunset time compared to what it should be doing in England, and that'll help you figure out where you are on the Earth. So it's pretty complicated. You got to know what day it is too, because day day changes around the course of a year. So it's not trivial. But the British Admiralty put a prize in place to try to figure this out, and some a guy and his son figured this out, and they developed these clocks that would actually keep time. That was the hardest part. Was if you can imagine a clock you have to wind, um, making sure you're winding it constantly, that and you have to keep it so that temperature fluctuations and humidity fluctuations, like you're on a ship that's rocking around on the ocean, doing all of that to keep things right. We have things really easy today because we can use GPS and it can tell us where we are based upon triangulating us from a satellite. All right, so this helps you figure out direction though. Like if you want to get from America to England, you know what angle and you know what distance you need to go, and it works. So that's pretty good. But it makes the Earth look pretty funny. So there are other kinds of projections that can do that. Now, probably one of the more common projections that we will work with and that you will do things for is what's called an equivalent projection. So this is a conic projection, and it preserves accurate area of a certain place. And so these tend to be these tend to be they work sort of up to continental scale. And so there's Albers equal area for North America works pretty well. Everything, it preserves area. Now scale and shape are going to be distorted, but the distortion is not too bad, especially if you're working within a along parallels. All right, so there's not much distortion this way. And so it works very well for east to west land masses, which is why it's good for the United States. If you're doing a project where you're trying to show what's going on in the U.S. and trying to show differences, or this is a good projection for that. Area is constant. You can measure things on here and know that you're going to be pretty accurate if you're looking at, say, the area of fires in California versus Texas or something like that. You can use this projection to do those kinds of things. So an equivalent projection preserves area, and that's a key point. Conformal projection preserves direction. Equivalent preserves area. And then there are compromise projections. And so these are not equivalent nor conformal. There is distortion in essentially every dimension. Size isn't right, shape isn't right, but it does look better. And that's the advantage of these projections. These are good choices if you're going to look at if you want to make a world map. Because at this scale, it really starts to matter. Things start to get off if you use other kinds of projections. So you use a compromise projection. Robinson is a pretty common one. And Robinson's a nice projection. It cuts off a little bit at the poles, but it gets most of the land masses here. You'll see that you can almost always find a compromise projection because the meridians are curved, and so you're stretching it less at the poles than you do at where you don't need to stretch it at the at the equator, but you're just stretching it less than you would if you were doing a Mercator projection or something like that. And so Robinson's a nice one. It's used by National Geographic Society. There are others. These are sometimes also called, besides it being compromise projections, they're often triple projections. So you're projecting in three different ways to try to make them look a little bit better. All right. So these are the three kinds of projections that I want you to know their sort of basic properties to. So know like how you can start the projection, whether it's planar, cylindrical, or conic, and then whether, because you can kind of do any of these in this way, and know the difference between conformal, equivalent, and compromise. Just what's on the slides. Not anything more detailed than that. I just want you to know the basics of these so that when you're presented with something. Now, what can happen in ArcGIS is one of the things you'll have to keep in mind is the source of your data, and this actually is a source of constant frustration for me. Is that you don't always know what form the data you've gotten is. You have a map, and it may be missing its projection file, or it may be just was uploaded to the internet without that. So you don't know what somebody did. So you can project it. You could tell ArcGIS to like, oh, make it Robinson, and it will. But if it was already projected some other way, it can put in place errors. As long as it has a projection file associated with it. So when we get into a little bit like what ArcGIS is doing underneath the hood, we'll look at a project file. You'll see lots of different files in there. And one of them is a .prg file, or PRJ file, projection, PRJ. And that is important to have, though they're all important because otherwise you lose information, lose data. But as long as it has that, ArcGIS can now on the fly adjust things. So if it knows what it is, it will set the map to whatever you bring in first. So that's important in some ways when you're building a project, is to decide what projection are you going to use and add some data that has that, or you can set it and you can always change it later. It's not that big a deal, but that's the way it defaults to. Whatever you put in first, it's going to treat everything like that. So if you're working like with a world map and you put in a world map that's Robinson projection, everything else it's going to adjust to that. As long as it has a project file, it can do that on the fly, and you will never notice any problems. But if it doesn't, it can start to cause problems. Sometimes it will just throw your data like way out in the middle of the Atlantic Ocean, and if it's not in the middle of it, you'll notice there's a problem. Like, why is this nowhere? Because it doesn't know where it should be. So that's one thing you may have to adjust because of that. It doesn't have the right coordinate system. It doesn't know where it's supposed to be. That's one thing. The other thing is that you'll start to see errors. Things won't line up. So you'll have houses that are in the middle of the street, or that they're, one set of data shows something here and another set of data shows the same thing over here. Like, well, why aren't they doing this? That's a projection problem. And so those are some things that we can look for and diagnose later on, which is why I spent some time talking about projections here at the beginning. All right. Now, there are other ways to make maps. There are sort of advantages and disadvantages. Another kind of map is called a cartogram. In this particular case, this is like a projection, but we are distorting things based upon geographic access to higher capability severe acute respiratory failure centers in the U.S. So where is it you can go if you're having respiratory failure? How easy is it for you to get to? And this is it's not a county level map, but it distorts the area. So if you're here, it makes the area bigger because there's more direct access. If you're out here where there's none, it makes the area smaller. And there's a little bit of a map of the outline of the United States behind it to try to give you how this distortion is taking place. You might see different kinds of maps like this. All right, so just to summarize, We're talking about when we don't need to worry about projections. Well, a lot of times, particularly if we're asking a question that's working at a large scale map, it doesn't really matter. If we're looking at the relative locations of things, it doesn't really matter because any projection they'll be in the same relative position. But if we're gonna measure things, we're gonna deal with things, it actually can make a difference. So the bigger the scale, or excuse me, the smaller the scale map, the more important it is to think about that. Okay, and so um, one of the other challenges is that there there you need to make sure you're keeping all your files organized. You're not deleting or moving things out of individual, what can look like on a PC can look like an individual file that you can actually go into, and then there's like lots of little things. And it doesn't look like that in ArcGIS, but it does in Windows. And if you mess around with that, you can cause problems. So don't do that. The other thing is that different agencies, even within like the federal, there's no like standard projection that the federal government uses. So if you're mixing census data with geographic data from the Department of the Interior, all of which may use a slightly different projection. State data, there's a state plane system, which is I find very annoying. I don't know why it still exists, but um, different states created their own coordinate system. Basically, so instead of having to use latitude and longitude, you can just use an X and Y number. And so every state has one of those. So if you're working in a particular state, and if you get state sourced data, it may be in state plane. Luckily, ArcGIS can handle all of these different kinds of things, and it's not much of an issue. So yeah, so census files. These are block groups. So the Census Department has divided the U.S. up into different areas that have roughly equivalent numbers of people in order to take the census. They use geographic coordinate systems, so latitude and longitude. City of Pittsburgh, like planning agency, uses a state plane coordinate system, so uses a separate set. And this is what you can look for in the properties of your files to find that in ArcGIS. So these are the same areas, right? So this is also Pittsburgh, this is Pittsburgh, but they're divided up a little bit differently. They use a different coordinate system. So figuring out which of those kinds of things that you're going to use. Okay, so yeah, this is what I mentioned earlier, is that when you put the first thing you put into to a new project is going to set the projection, and then everything you add to it will adjust to that. All right, so they in this one they put sidewalks in that were done that have a state plane coordinate system associated with them. Then they added in block groups, those census blocks that are added on there, and they all line up because ArcGIS knows how to handle these things and is now powerful enough to do it all the time. When I first started a long time ago, you would actually have to make sure you would project all of your stuff the same. So you'd have to go through that step and do it every time to make sure you had data in that format you wanted to use. And you'd maybe save multiple copies of the same data just projected in different ways so you could add the right one that you wanted to your system. You don't have to worry so much about this. Less of a problem. If things start showing up funny, I'll take a look at it. We can try to track down what it is. It's basically that. So the last thing I wanted to show is this. This is a comic that's only funny to somebody who likes geography. But is anybody familiar with XKCD or a web comic CD? They do a lot of science comics. So if you like, jokes about physics, I highly recommend checking them out. Their archives. There's a lot of different ones, and this is one they did about what your favorite map projection says about you. So I think this is a link. You can actually get to their site here. Yeah. So you should be able to click on this in PowerPoint if you want to go and look at this a little bit bigger. There's some inside jokes about different kinds of projections and what they are like. But this I like shows the reason I bring this up is it shows some different ways that people have approached making making different kinds of projections. Right. So there's a Mercator and there's Robinson. Those are two ones that we've talked about. Um, there are more complicated ones that um, cut up the earth in different ways to help preserve shape a little bit better, and different orientations. You can center the map over a pole versus over the equator. There's all different kinds of ones of these. The reason this one has a bit of a history. There was a movement in geography to make, because the Mercator projection overemphasizes the poles, and everything along the equator, while it's not distorted, is not the same size as this. Um, there was some thought that this biased people's perceptions and devalued, countries that were along the equator or near the equator. And so this projection was a way of dealing with that, which and so there was like a lot of uh, just it was sort of a there was like a lot of argumentation that happened about this, whether that was necessary. But the problem was, it was kind of a silly argument, because actual geographers don't care about, they pick a projection for a reason. It's not to how necessarily to make how the earth looks, but in some cases it is. Um, but most geographies don't use Mercator for anything, because it's only pretty much useful for navigation. Things don't look right, and areas are radically distorted, so you can't measure things. Geographers have a reason for picking a projection, and it's not usually how the map looks. In some ways it is, but it's not always. Okay, any other questions about maps? Okay, so let's stop there.